the one monolayer of material on the surface tends not to work so great. What people then came up with is that let's put on the surface some polymer into which our catalyst is incorporated. And that maybe works better because instead of a single monolayer of the material, now we've got a large volume of material that the reaction can occur with. And so the reaction is much more like the solution phase reaction, but still the material is confined to the electrode surface, so we can keep it there and have the good advantage that has. So polymer modified electrodes are often used in this same way. So for example, if we want to reduce molecule P to Q, what we can often do is, we want to reduce molecule A to B. The idea is that we can generate a reductant in situ, Q, that will do the job for us. So the desired reaction is A to B, which may or may not be available at the electrode surface, maybe have a high overpotential, but we can generate in situ the reductant Q, and if it's in the polymer, bound to the polymer, then we have it stabilized, and then that can react with A to do the job. So the idea here would be you'd have an electrode, you'd have some polymer modified surface inside the polymer. You'd have molecule P, which can undergo an electron transfer at the electrode, which leads to Q. Q can do a job on molecule A that diffuses into the polymer, reacts with Q, forming B. When that happens, that regenerates P, and the cycle can repeat itself as long as there is A available to regenerate P. We'll continue to get electron transfer in this way. Of course, to have that work, P has to have a larger reduction potential than A in the first place. It has to be a stronger reducing agent than A is. So the questions when we want to make a polymer film like this, the question is, how does A get into that polymer film, and how can it react with that molecule Q? How can we generate Q? How do we get electrons from the electrode surface to somewhere out in the polymer to get to P? And once we've got those electrons out to P, how does the incoming material A get to Q to do the reaction? And how does then, once the reaction occurs, how does B exit, and so on? So those are all functions of the type of polymer modified surface we've got, and so on. So let's briefly summarize our different polymer types, and we can talk about polymer modified electrodes, but they're really all lots of different kinds of polymers. So let's briefly discuss some different ones. One type that's kind of interesting is the electronically conducting polymers. This is now getting a quite wide number of these types of polymers, in which the structure, the electronic structure of the polymer itself is such that it is electronically conducting. In many ways acts like a metal material, really probably more like a doped semiconductor material, in which it can be induced to conduct pretty well. Not as well as a metal usually, but pretty well. There's some polymers based on polyacetylene that are very highly conducting if they're made properly. Polythiophene, polyfuran, what's the other one? Polypyrrole are all materials that can be induced to become conducting once they're in the polymer form. Well, one example I've got is the oxidation of pyrrole. And this usually has to occur in acetonitrile or MECN. And you can do it in different electrodes, but examples at platinum. What you see is once you oxidize, basically what you do is you put pyrrole as a monomer in the solution, you oxidize that material on the electrode surface. During the process of oxidation, you make this conducting film, and so the oxidation can continue on the surface of the polymer film itself. So you continue to oxidize the material initially on the metal surface and then later on as an additional coating on top of the pyrrole film. So you can get the thickness of the film by counting the amount of charge that you've passed in there and so on, and you can tell how much material you've actually oxidized. Once you've put a substantial quantity of pyrrole on the film and you do the electrochemistry of it, if you do a cyclic voltammogram, and here we're going to draw our axes in the opposite way because that's the way that was in the reference. What you see is initially the material is insulating when you have a negative electrode potential applied to it. Then as you increase the potential in the positive direction, you get an oxidation current, you get a little peak, and you get this kind of a odd shape to it. And you get a region in the positive part of the quadrant in which the reaction, in which you oxidize the polymer, now it becomes electronically conducting. And that electronically conducting polymer acts like a metal in many ways. You can support additional electrochemistry on the surface of that polymer and so on. This particular thing came out of a paper by Diaz and Castillo, the Journal of Chemical Society and Chemical Communication in 1980. And the conduction occurs because of the electronic structure that you form once a polymer. And basically, you can think of these as extended conjugated carbon bonds. And so that extended conjugation allows the electrons to be delocalized, and so the molecular orbitals become overlapping, and you can get electron transfer that way. Now, once you form that, what they call that by the oxidation, the physicists that are doing this often call this process doping. So they've doped the polymer film into conduction. Really what you're doing is you're oxidizing it, so it's just difference in terminology between the physicist and the electrochemist and the chemist. This is simply an oxidation. You've removed one of the electrons from the backbone of the polymer, and that allows the conduction to occur. Once all the electrons are filled in the polymer, there's no room for additional electrons, so that you don't get an electronic conduction that way. Once you've done this, you've actually added or taken an electron away. So additionally, you have to also consider the fact that ions have to move in and out. Once we've put a positive charge on here, we have to have negative ions coming into that polypyrrole film to do the reaction to allow it to occur. If you don't let negative ions come in, you won't see any oxidation or very little. And so if you could actually do this by making very large negative ions that just physically can't incorporate into the polymer film, in that case you don't see this sort of behavior. It just doesn't occur. But once you put a smaller negative ions like chloride or something, they'll scoot right in and do the reaction that you need. All right. So these would work in the sense that they could be thought of as new types of metal or new types of electrodes. So sometimes reactions work better on certain types of electrodes than others, so these could be a different sort of metal electrode or electrode you could think of that you can do experiments on. What about another type of polymer that's similar to this but not exactly the same? They're called redox polymers. In this case, the polymer backbone itself is not have incorporated into it this extensive conjugation, but the polymer has in it oxidizable and reducible species that allow the entire film, a large quantity of material in the film, to become oxidized or reduced. So typically what you would do is have the polymer, and then hanging off the polymer you would have covalently attached to it some sort of material. A very popular set of materials are based on this bipyridyl backbone. Often abbreviated BIPI, and there's a vinyl bipyridyl group and vinyl bipyridyl groups that you can also think about. Once you've attached this bipyridyl group, what you can do is you can put in a ruthenium ions, and the ruthenium are strongly covalently bonded, or not covalently, but strongly coordinated to that those nitrogens. And so the idea would be that you would have a polymer with these bipyridine groups on it, and then the ruthenium molecule can come in and become complex, and then you can do the electrochemistry of the ruthenium, typically a ruthenium 2,3 type reduction. So you'd have this polymer, and you could think of it as having a ruthenium 2 on it, or a ruthenium 3 attached to it, and you can put an electron into the ruthenium 3, converting it to ruthenium 2 in the chain. Now this is different than the electronically conducting polymer because we're not, the ruthenium 2 is not part of the polymer itself. It's an additional thing we've added. We can put different ions in there often, like something like osmium is often used also as a material. Now if you have a lot of this ruthenium in the system, you can think of it in an interesting way. You can think of how does the reaction can occur. Well, you can think of it as a reaction in which we take and have an electron get transferred from the ruthenium 3 to a ruthenium 2, or you convert a ruthenium 3 to ruthenium 2, and the energy for that is through an electron self-exchange with another ruthenium 2 somewhere else. So you can think of, in the process of converting this material, we can convert a ruthenium from a ruthenium 3 to a ruthenium 2. We can convert a ruthenium 2 to a ruthenium 3. And that process can occur throughout the chain, like so. So what you can do is you can propagate an electron from the electrode surface by a series of electron exchange, self-exchanges. So you put an electron in to ruthenium 2 or ruthenium 3, which makes ruthenium 2, and in that process, that electron can then convert a ruthenium 2 back to a ruthenium 3, and so on as you get the system propagating along, and so until the end where you might have a solution phase at the very end. So this process of electron self-exchange is called electron hopping often. Because the electron really doesn't physically move, it just gets transported from one redox center to the next. And so in this case, we don't really have to have a movement of charged ions in the system to do the electrochemistry. Now, the amount of this that happens is going to be very significantly affected by the amount of ions that move in and out, because if we put an electron in, we still have to have a positive charge at the other side to be compensating it for it. And what the rate of electron exchange is. So we need to know, for example, the rate of exchange for A and A minus going to A minus plus A. And in some molecules, that reaction is quite slow. In the Rubippi process, it's a little bit faster. That's why they use ruthenium as a molecule. And you also want to know reactions like this, where A plus B being oxidized and reduced to, say, A minus and B plus. Now, a solution species coming into this sort of system would hijack that electron exchange chain. And so it would sit in here, come in, and the electron would not transfer to, say, another ruthenium, but it would transfer to the solution species that has permeated into the film, picked up an electron, or transferred an electron, and so on. Once that electron gets in the film, it can be transported back to the electrode through this polymer cycling, this redox polymer cycling. So redox polymers are different than conducting polymers in that the backbone itself is not conducting, but material that we've attached to it is electronically conducting, not electronically conducting, but can conduct by this electron exchange mechanism. So the conduction in redox polymers is by a mechanism of electron exchange rather than by this overlap of molecular orbitals. Number 3 type of molecules referred to as polyelectrolyte films. These films, in this case, act as solid electrolytic solutions. And so the materials are in there, and the reason they stay in there is that because they are either electrostatically attracted to that film material, and also because they don't tend to diffuse very rapidly in the solid polymer matrix. A very common polyelectrolyte is a material called naphthalene. It's made by DuPont. There are some variants by other companies, but naphthalene is a very famous one. And it's basically an ion exchange membrane. The idea is that we've got a backbone. It's kind of like Teflon in the sense that it's got a carbon fluorine backbone. Let's try that again. Like so. But every so often it has a pendant group on it, which is this sulfonate group. And naphthalene has basically a backbone like this. It's got this so this sulfonate group that's sitting at the end of the polyelectrolyte chain is normally going to have, well, it will always have some sort of compensating ion associated with it. Now in the dry form of this material, that associated ion is probably sodium, and that's where the naphthalene name gets, that source naphthalene gets its name from. It's the engineers that made this or were working with this realized that it was a sodium attached somehow in this backbone, and they knew it was with the sulfonate, but so they made it in the sodium form, so that was a naphthalene form of it. But you can exchange the sodium by putting it in a very high concentration of protons in a very strong acidic solution and make a protonated material, or any other really sort of cation associated material by adding a large amount of excess amount of other ions. What you can also do is add other types of cations to the system. For example, you could add in this Rubippi complex. which would have a 2 or 3 plus state, or osmium-Bippy complex. Or you can add in things like ruthenium hexamine, and so on. All kinds of things that have positive charge are easy to be incorporated into this film because all they have to do is knock off a sodium from the association of this and then be attached. And because these have high positive charges, they're going to be more strongly attracted to that sulfonate group than a sodium ion would be. On the other hand, anions cannot easily be incorporated into this film because they're going to be repelled by the backbone negative charge. So these ions are incorporated in the film now by an electrostatic attraction. That's not a covalent bond, though. It's not even a complex bond, so they can actually move around. They can move by, say, coming off one sulfonate and going to another sulfonate. So they can physically transport themselves in that film. It's nice because we don't have to make a special redox molecule to be attached to the system. Unlike in the redox polymer case, we had to physically change the type of bipyridine by adding a vinyl group on there so it could be incorporated into the polymer itself. Here, we don't have to. We can put in any sort of cation that's electroactive and investigated on that side. And so how does the electron transfer occurs? Well, it occurs in the similar sort of way as that we had with the redox polymer membrane. We can have electron hopping, electron self-exchange, but because we've also got the ability for these materials to move, they can actually physically diffuse through the polymer. So in polyelectrolyte membranes, we can think of the Rubippy, again, these are acting as catalysts. That's what they're there for, to catalyze chemical reactions, oxidations, reductions. But they can move either by the charge can move through the film by electron hopping or by physical diffusion. And usually it's a combination of both types of motion. Depending on the rate of electron self-exchange, the electron hopping may be very slow or very fast, and that will dominate perhaps the other sort of thing. So naphthalene is a very popular polyelectrolyte for materials. It's used for lots of things like fuel cell membranes and so on to allow protons to pass through and exclude the anionic component and so on. Another material people have used, polyvinyl alcohol, polyvinyl pyridine, for example, has cationic sites on it. The pyridine becomes protonated and it has cationic sites. And so it can incorporate anions like ferrocyanide or iridium hexachloride. And so on. There's also PEO is a popular one, polyethylene oxide, also another nice, has nice properties. I thought I'd take time to do a little detour. We've talked about these redox polymer materials and polyelectrolytes and so on. Let's demonstrate how you make them, or at least discuss how you make some of these polymer-coated electrodes. There's a couple different ways. One is a dip coating. The idea is you put the polymer dissolved in a suitable solvent, and at a certain concentration you dip your electrode into the solvent, and a thin film of solvent plus dissolved polymer is attached, or not attached, but is incorporated as a thin film of solution on top of the electrode. Then you allow that to evaporate usually. And so the solvent will evaporate, leaving the polymer behind to form an adsorbed polymer layer. Once polymers adsorb on surfaces, it usually have to have a very good solvent to remove them because they're not going to tend to dissolve in, say, or aqueous systems. There's just not enough solvating power to get those materials to be dissolved. A second idea is just add on a single drop of material and let that evaporate. That tends to make a pretty crummy surface, actually, because it's hard to get a good, accurate amount, and the film tends to be irregularly in thickness. So you form a little drop on the surface, and then when it evaporates, you tend to get stuff like this, where it has formed a sort of a central depression or a central thing. It's hard. It's not uniform in thickness. Oxidative or reductive deposition. For example, the polypyrrole is a oxidative process. Polyaniline is also an oxidation of aniline. Can be made. You can make a polyaniline film. A very common one is, and very good way to do it, is called spin coating. Requires a little bit more of equipment investment. You use what these call a spin coater. It looks a lot like a little bit of just a spinning chuck, and then you put your material on it. Usually it's got a little vacuum pressure to hold it down. So you might take your electrode and you put it on top of this chuck, which has a rubber end or an O-ring, and then vacuum. And then that spins at a certain revolution per second. You add your material at a certain rate, and centrifugal force tends to spray that material out, and leaving behind usually a pretty uniform film. So this is a nice way to make nice uniform films that are particularly uniform in thickness. Okay. All right, let's go back to the idea of charge transport. In redox polymers. What we can do is, when we look at charge transport, we can think of the charge as having some sort of a diffusion coefficient. And in this case, the diffusion coefficient is somewhat fictional. Well, it's really all fictional, because the charge does not necessarily move like a molecule or ion in solution will diffuse through the solution. But because it has all the other properties of a moving charge, we can assign a fictional diffusion coefficient to it. So it's one way to study it. And so that fictional diffusion coefficient of the charge moving through this redox polymer can be called dCt. And the rate of a polymer film oxidation reduction is going to be proportional to dCt to the 1/2 power times the concentration of redox centers. Okay, what are we talking about? We're talking about, we have a polymer film on the electrode surface. We've got a redox active polymer into it. And what we're asking ourselves is, what's the rate of propagation of that charge through the film? At what rate does that charge diffuse through that oxypolymer film. And we want a fairly rapid diffusion coefficient because that will be an efficient way to oxidize or reduce material coming in and out of that film. But we can study that rate by knowing that we can, by putting together a fictional diffusion coefficient, which is a reflection of the rate that the charge transport moves through there. Not assuming a mechanism of movement of charge, but assuming that it does move, we can assign a diffusion coefficient to it, and multiplying that by our number of redox centers. And we can calculate that by knowing how many, for example, how many bipyridine groups that we've attached to the polymer backbone per a certain number of carbons otherwise. And an example of this is, was by Anson. Anson is another guy, Fred Anson at Caltech, very famous electrochemist, been around a long time, working in collaboration with Savient and probably a postdoc, I guess, Shigehara in 1983. This is a little old, but this is in JACS, volume 105, page 1096. Now they put a film on the electrode surface, and they're using a rotating electrode, and we're going to talk about rotating electrodes next time, but the idea is the rotating electrode allows the mass transport of material from the solution to the film itself to be uniform. Unlike a planar diffusion system where the mass transport changes with time, here we've got a uniform movement of solution. So we've got a film on the electrode surface. Now, if the rate of if the electron transfer process was not limited by the rate of charge transport through the film, you'd expect to see an increase in current for our, say, the limiting current on the wave for some reaction that we're catalyzing that's proportional to omega to the 1/2. And we'll see this in the next little bit. But omega to the 1/2 is a rotation rate. And so the faster we rotate this electrode, the faster the mass transport should be. So in an ideal case, we'd see this sort of behavior. The current would tend to increase linearly with the square root of the rotation speed. In practice, what they saw once they put their the redox film on the system is behavior like this, which suggests that there is a mass transport limitation. In fact, the mass transport is not mass but charge in this particular case, because we've made sure the mass transport would, and this would be the case for a bare metal electrode on the surface. So in that regards, we're now having a limiting current that's limited not by the rate of mass transport, but by the rate of charge transport through the film. So we'll get a limiting current here, we'll get a limiting current here, we'll get a limiting current here. So what's the difference? Well, we can break that limiting current down into two components. One, a limiting current that's due to the mass transport limited current we'll call A, which is the bare electrode current. In other words, the limiting current you'd see if there was no film there. And the limiting current that you do see when the film is there. And what you find out is you plot that 1 over the limiting current versus 1 over the rotation rate, you get a straight line. And the intercept of that line then gives you the rate of charge transport through the film. So once we know the rate of charge transport through the film, we can use that to use our we can use the equation that we use for mass transport limited systems, but we would replace this mass transport limited process by this term here, and that would give us the effective diffusion rate through the system. Well, actually, the MC would be this part here. Okay. 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 I think we'll Okay, let's talk about one more thing. It's a little trickier idea, but let's take another example of a material. And this is, in fact, what Anson did. They used a polylysine film. And a polylysine film is similar in some respects to the polyvinyl pyridine. It's an anion exchange material. And the backbone is a polymer like so. With a pendant group attached to it, 4 methylene groups, ending up with an amino group that is normally has a bromide ion as the countering charge. Now, within this material, we can think of the polylysine as being a large piece of spaghetti that's all throughout the material. Now, some of it may or may not be attached directly to the electrode surface at the electrode. But if we think of this surface, we can think of it as this polymer film. We can think of it as having 2 distinct regions. One outside, well, actually, we can think of it as 3. There's a bulk solution outside the film, in which the polymer film has no particular effect. Inside the film, there is a region that you can think of as being between the polymer strands. And we can think of that region between the polymer strands as being very similar to the bulk properties of the solution. But nearby the polymer strands, there is a region that they call the Donan domain, where ions will be affected by the presence of our ion exchange groups on the polylysine backbone. So charge transport in this polymer film can occur by materials diffusing around in the bulk areas between the polymer strands, or by being associated with the Donan domain near the polymer strands. So we've got in the bulk, in this thing, we've got this 2- charge, and then we can associate it, or 2+ or plus charge, I should say, and then we can associate it with ionic groups. And in that Donan domain, we're going to attract anion counter ions, and we're going to exclude cations from that system. And they used in this system a test molecule that was an iron 3 complex with EDTA. So they used Fe3 EDTA, we'll call that Z-, and iron 2 EDTA 2-, we'll call that Z-, for compactness of the notation. So in principle, we should see 3 types of diffusional effects. If we didn't have any polymer films at all on the surface, we'd see a diffusion that would be characteristics of the bulk solution. And so we can call that a current that would be associated with I sub s, diffusion outside, I sub E we can think of as the current that's associated with electron self-exchange. In other words, the exchange, well, not self-exchange, but exchange between the polymer-bound redox-active molecules. In other words, the rate of self-exchange between iron 3 and iron 2 during this electron hopping. And in the donut domain. And I sub k would be a place exchange between the donut domain and the outside solution. And this is often associated with ion hopping, not electron hopping, but ion hopping, where you could go from site to site by hopping along the charges. So instead of diffusing around in solution and coming up to a site, you'd actually just physically hop over, not hop, but it just moves sort of along as like beads on a string along that collection of positive charges. So we can write relationships for those different currents. We can say that I sub s was the Faraday, the diffusion coefficient in the solution, a K term, which is a partition coefficient, concentration of species A in the bulk, and divide through by phi, which is the film thickness. So the amount of material is going to be related to how diffusion, the current in the film that's not in the donut end is going to be related to how thick the film is, obviously, what the concentration is outside the polymer material, what the partition coefficient is, in other words, what's the relationship between the amount of material at equilibrium in the film and in the bulk solution, the concentration ratio, and the diffusion coefficient outside the polymer film. So basically, all these other parts are scaling the diffusion coefficient that way. I sub E is going to be related to the Faraday, the diffusion coefficient in the donut domain, in that domain right next to the electrode surface. Whoops. The charge, or the amount of absorbed material of species Z minus and divide through by the square of the thickness. And IK, I kappa, is the apparent rate of this electron hopping process times F times the material in the absorbed on the film. So in other words, the exchange of so on. If we plot the current density versus the film thickness, we'll get a kind of a diagram that describes how something would behave under these conditions. And we'd get two limiting cases. One in which we have a very thin film. That's probably in centimeters. I don't know what that would be. In that case, for a thin film, the current would essentially be equal to I sub s. The total amount of current, I sub f, would be the same as the diffusion coefficient in the film outside the donut domain, because there's no time for exchange to occur. The material comes in and just goes right through. When that material becomes quite thick, then we have a large amount of time for this reaction to occur, and so there's going to be able to support ion exchange between the donor domain and the film solution inside the film. And so the total current is going to be equal to IE plus IE plus IS. And this would determine, the exchange rate would determine what the value of IE was. So that would be something you could determine in that particular case. And then you'd get an intermediate region between those two. When they did this experiment with the iron EDTA and using this analysis to determine what these different parameters were, they found that the d sub s value is 2 times 10 to the minus 6. D sub O is 4 times 10 to the minus 6, and that was the bulk diffusion coefficient. And D sub E is equal to 6.7 times 10 to the minus 6. And these all have centimeters squared per second. And K is equal to 1, the partition coefficient. So what's that tell you? Well, what it tells us is that the exchange process of allowing material to move by charge transfer within the donor domain is a fairly efficient process. It increases the diffusion coefficient you'd see from the bulk by quite a large amount. And the diffusion coefficient inside the film, but without not being in the donor domain, is not very efficient. So all the charge transport in the film, well, most of it is occurring by charge transport within these donor domains, by charge transfer, electron hopping between the two sides. Very little of it is occurring by the bulk material diffusing through the between the polymer film material. Okay. Well, let's stop here and we'll take a little break, and that'll be it.